So section 1.7. So when we're talking about combining functions, for the first part of what we're talking about, what we're interested in is arithmetic. And then we'll talk about another way of combining functions, but nothing really new. But before we get into it, why would we want to combine functions? Why not just leave them separate? Yeah. Makes some things easier to do. So just like that was kind of the point of the joke I told last Friday about the mathematician moving the coffee pot to the other burner. We turn problems that we don't know how to solve into problems that have already been solved. So if we can take functions and combine them, instead of looking at these little individual pieces, we can think about them as this one big thing, and we can treat the one big thing the same way as we treat the little individual things. It makes our lives easier than treating them as individual little separate things. What are other reasons? Any ideas? Yeah? Anyone? Another reason that we combine functions is that we can make up more complicated functions out of simpler ones. So we can build up these functions out of simpler pieces. So we can make more complicated, more interesting functions. And it is sometimes, or often, it's more useful kind of to go the other direction and look at a complicated function as made up of these smaller individual pieces. So we can also break the function apart. And we'll talk about one way that we're going to do that today as well. Anybody think of another reason? I think the main reason is this. All right, so arithmetic. We're talking about adding, subtracting, multiplying, and dividing. So we're going to say f and g are functions. And they're nice functions, so their domains overlap, so they behave nicely. F and g are functions. We're going to combine them in several different ways. F plus or minus g of x. Now this is f plus g of x or f minus g of x, not f plus g times x. Well, what this is, all we're doing is adding or subtracting those functions to each other or from each other. So when we're talking about nice functions, when we're talking about adding or subtracting, what's the kind of the everyday language we use for doing that? When we're adding functions together or subtracting. So let me give you an example. What about something like 2x plus 5 plus the quantity x plus 3? When we add those together, what do we call that? That was when we'll talk about that in multiplication. So what do we do with that 2x and that x when we add them together? What do we call that? Combining like terms. Yes. So when we're adding, subtracting, essentially we're talking about combining like terms. So it's something that we've been doing for a long time. We're just making it a little more formal now. Combine like terms. F times g of x is f of x times g of x. And when we talk about multiplying functions, what are we going to be doing? Distributing. And especially with polynomials, what's our little acronym for remembering how to distribute correctly? FOIL. Yeah. FOIL is an acronym to help us remember how to distribute correctly when we have multiple terms. F, the last one for our arithmetic. F divided by G of x is f of x over g of x. But what do we have to be careful with here? G of x? What about g of x? Yeah, we don't want g of x to be 0. We don't want to divide by 0. At the end of the year, we'll do a little introduction to some of the ideas that you'll use in calculus, and we'll talk about a kind of a trick that lets us sort of divide by 0, but not exactly. So people joke that the calculus, the point of calculus is little tricks that let you divide by 0 and multiply by 0. Kind of interesting. All right, so I'm not going to do a bunch of examples of adding and subtracting and multiplying and dividing functions. I think we probably can do that fairly well. All right, so we're good there. Okay. The next way that we're going to combine functions is called compositions of functions. So what do we mean in kind of an everyday language when we do remember what we mean by compositions of functions? Has to do with the specific groups. It has to do with a specific way of grouping them. Yeah. Plugging functions into each other. So I'm going to say a function into a function. We call that a composition. And our notation for a composition is f of g of x. And what this means is we're plugging g of x into f of x. So instead of using x as our variable, we take whatever the function g is and put that in the place of every variable. And g of f of x, we're plugging f into g. And in the compositions of functions are I'm not going to say more useful than the other kinds of combinations of functions, but they usually tend to be more interesting in terms of how they work and what you do with them. All right, so let's look at an example of doing a composition, making a composition. So let's say f is x squared plus 2x, and g is 2x plus 1. We want to find f of g, and I'll use the notation. I'll put the function notation, and g of f of x. I think our book always puts the variable in there, but it's not incorrect to say just f of g and say the variable x, your variable is assumed. But I think our book always uses the variable. All right, so f of g of x is f of g of x. I'm just writing this explicitly. So this is telling us everywhere we see an x here, we plug in g. So that's going to be 2x plus 1 squared plus 2 times x plus 1. And now we're just going to use our usual ways of combining functions. First we make the composition, and now we're going to multiply this out. So 2x plus 1 squared is 4x squared plus 4x plus 1. Remember, 2x plus 1 squared is 2x plus 1 times 2x plus 1. We don't want to harm the puppy and say that's 4x squared plus 1. So please don't harm the puppy. Plus, here we're going to distribute 2x plus 2. Now, I don't expect you always to write out all these steps like this. Yeah?
Should it be 2x plus 1 instead of just x plus 1?
Oh, yes. Did I forget my 2? Thank you. When I make mistakes like that, I'm glad that happened today. I'm seeing if everyone is paying attention. Trust me. All right, now we're going to combine like terms. So we get 4x squared plus 8x plus 3. And that's our composition. So I wrote out all the steps explicitly. You don't necessarily have to write out all the steps explicitly. I just wanted to show the whole process. All right, and g of f of x is g of f of x. And this, we're going to take f and plug it in for x, plug it into g. So that's going to be 2 times x squared plus 2x plus 1. So we get 2x squared plus 4x plus 1. And we can see that those are not the same. In general, g of f doesn't equal f of g. Fancy way to say that is composition is not commutative. Something special happens when g of f and f of g both equal a specific thing. We'll talk about that next time. All right, we good here? One thing we have to be careful with compositions is the domain of the composition, because there are two things that are contributing to our final function. So I'm just going to make a note here and say the domain of a composition is restricted by the final composition and by the inside function. And what I mean by inside function is the one that we're substituting into the other function. So the easiest way to see this is with a couple of examples. So let's say the problem, you might get a problem that says f of x equals 1 over x minus 2 and g of x is square root of x. And we want to find f of g and its domain. Yeah? Oh, thank you. All right, so the composition, f of g of x, this is pretty straightforward composition, is, I'm going to taking g and putting in for x there, 1 over square root of x minus 2. And here it's pretty easy to pick out what we're going to restrict from the domain. So what are we going to restrict from the domain so that this function is nice? We're going to say, yeah, we're going to say x not equal to 4. But when we plug in x into our function, we're plugging it into g first. So we have to pay attention to the domain restrictions of g. So what do we have to restrict from the domain of that? Negative numbers. So we're going to have to say x greater than 0. So these are our restrictions. So our domain would be all real numbers except. So our domain would be all real numbers except x not equal to 4 and x greater than 0. Yeah?
Couldn't x also equal 0?
Yes. Greater than equal to 0. Thank you. So we have to take into account what we want to restrict out of the final composition and the inside function. Here g is our inside function. Now this one is easy to see. Well, let me change up the example a little bit where we have to be a little more careful. So I'm going to say a and b. Here f of x is 1 over x squared minus 2. And g of x is the square root of x. So f of g now, we plug this in here, and we get the square root of x squared. We just get x. So if we weren't careful, we would say, what are we restricting from the domain of the composition? X not equal to 2. But we are careful, and we realize that when we do a composition, we're plugging our number into g first, and then putting that into f. So what do we have to restrict from the domain of g? Negative numbers again. So we'd say x greater than or equal to 0. So we have to pay attention to the final composition and the inside function, the function that we're plugging into the other function. Because when we do a composition, we're always putting our number into that first function first, and then putting it into the other function. So this doesn't come up a lot, but when it does come up, it's important. All right, questions there? Everybody good? All right, the last thing, and probably what's going to be more useful as you move forward, compositions are useful, but the technique that we'll talk about next is useful. Undoing. Compositions. So like I said at the beginning, sometimes it's beneficial to build up a complicated function from simpler functions. Other times it's beneficial to be able to take it apart and make a function and look at it as being made up of easier functions, simpler functions. That's what we talk about, sort of what we're talking about when we're talking about undoing compositions. So it's easier to see this by doing a couple examples. So the question you might be asked is find f and g so that the composition is 1 over the square root of 3x plus 1. So we want to find the two functions that we can put together as a composition and end up with this. So what's the easiest way to do it? What could f of x be? We could say 1 over, did you say square root of x? All right, that's one way to do it. 1 over square root of x. So then what would g of x have to be? G of x would be 3x plus 1. And then when we made that composition, it would give us this. And kind of the way we refer to this is the, and I've talked about it this way already, this is the inside function, and this is the outside function. And depending on the problem that you're trying to do, this might be a beneficial way of separating out those two functions. Is there another way we could do it? What if, yeah? Okay, that would work. F of x equals x, and g of x is that whole thing? Yeah. So that's another way to break it down. And again, this is the outside function, inside function. Is there still another way? Yeah.
Have f of x be 1 over x.
1 over x.
And then g of x be
So there's a third way that we could do this. And depending on the problem that you were applying this to, one or the other is going to be more beneficial. So there's not, for some of these, there's more than one correct answer. All right, questions there. Okay, let's look at one example that's a little trickier. Not too bad. Same thing. F of g of x equals, what do I want it to be? X squared plus 1. Sorry, x plus 1 squared minus x minus 1. We want to find f of x and g of x. So looking at that first term, what does it seem like that inside function, that g of x, should be? It seems like g of x should be x plus 1. Is there a way that we can make this other piece have an x plus 1 also? Factor, yeah. Minus x plus 1. So that would make f of x x squared, right? Minus x. And then when I plugged in x plus 1 for x, I would get this. There may be other ways to undo this one, but this is the one that seems like it's the most, makes the most sense, to me anyway. So this, when you start working in calculus, this skill, figuring out the inside function, outside function, undoing these compositions in your head is going to be an important tool. All right, are we good? We're good there. Okay, the last thing that I want to talk about, I just want to do a couple of examples. This isn't really new information, but students always, with this homework, they get intimidated when they see a graph. Actually, often in homework, students get intimidated when they see graphs. So I want to do a couple of examples that have to do with compositions or combinations of functions with graphs. Graphs are nice because they give you so much information. You just have to know how to get the information. So there's f of x, and just making this up, this is g of x. And I'm going to say this point, there's x equals 5, and this point here is 521. Sorry, want that to be 15. And this point x equals 5. I'm going to say this is 5 comma 15. And the problem asks us, using the graphs, find f of g of 5. Well, we know that f of g of 5 means the other way we can write that is f of g of 5. Well, what's g of 5? 15. And what's f of 15? 21. So when you get a couple of graphs of f and g, don't be intimidated when you see graphs. It's okay. All right, the last example. Let's say we have two graphs on the same set of axes. See if I can draw a decent picture here. And these points are supposed to be, the peaks are directly vertical from each other. All right, I'm going to say this is 5, 7, and this point is 5, 10. And this is f of x, and this is g of x. And the question asks us, using the graph, find f plus g of 5. Well, we realize that f plus g of 5 is just, what do we do with those two values? F of 5 plus g of 5, right? F of 5 is 10, g of 5 is 7. So what this problem really was asking us to do is add 10 and 7. So when you see graphs, don't worry, don't be intimidated. Graphs are your friends. All right, we good? Okay, homework. All right, and I've tried to fix all these little things. Notice on the board it says 1 through 6, comma 7. So I'll just write 1 through 7. What I do, when the problems are in a different section, I kind of think of them as different things. So that's what happens when you see things like that. For this particular homework assignment, I just picked out a variety of problems, so it wasn't easy to do like 1 through 17 odd, that kind of thing. All right, there we go.